Hi everyone. Today we are going to be taking notes on inverse functions. You should have printed the PDF if you could, or opened it, and hopefully you can either annotate on it or you can use notebook paper to take some notes. I'll be going through the PDF in this video, and then if you need to pause anytime, if I go too fast, just pause the video. I'll be asking you to pause the video to work out some problems during it, and then we will come back together to finish up the lesson. So our objectives for today are to write the formula for the inverse function of an equation, for the inverse of an equation, visually determine whether a graph is one-to-one, which we'll define today, and then determine whether two equations are inverses of each other using compositions, which we have just been learning. So it's all going to connect today. All right, now what an inverse is just remember the movie Freaky Friday or the song, either one, where two people switch places and they just take on each other's roles during the switch. That's basically what happens during an inverse. We have the domain and the range, or the x's and the y's, switching spots. So I'm just going to write the word switching. Can be found by switching, make sure my grammar is right, the domain and the range, or just all of the x coordinates with all of the y coordinates. And it's very simple if you have just the relation itself. We can do it algebraically, and we can look at it graphically or visually. So if two functions are inverse, then they will be symmetrical. Oops, that has two m's. To the line y equals x. So I'll show you a quick picture of what that would look like. We have a graph. Here's the line y equals x. And so that would just look like if I had, one graph over here, then I would have the same thing over there. And it would look, I could fold that y equals x up down the middle and it would match. The notation that we use for inverse functions is we're still sticking to the f of x style notation. And so it's f inverse of x, like that. So we have like an exponent or a superscript of -1 for inverse. Okay, so we'll start with graphically because that's the simplest way to draw it. So with an inverse, let's see, we have this purple one already. So we're going to use the purple. Let's identify the ordered pairs. So we have 1, 0, 2, 1, 5, 2, and 10, 3. And so what the inverse will look like when we switch, still going to use x and y, so it's conventional. What I'm going to do is I'm just going to write all of the y values in the x column and all of the x values in the y column. And so now we'll plot those ordered pairs. 0, 1, 1, 2, 2, 5, and 3, 10. And then I'll do my best to connect those. There we go. And now this is a much better picture than I just drew, where you can see the line y equals x. I'll put a little note here for that. And that could be folded, and those two lines would match up. Now, I haven't really done much with range yet. So we've talked about it on the basic functions, but we've been sticking to a lot about domains. So we're going to do the domains first of each one. So we're looking at this graph. The domain is from 1, and we do have a value at 1, so we'll use the bracket, and we can add an arrow to there, to infinity, always a parentheses with infinity. And then we can look at the blue one. There we can see that the graph starts at 0 and then goes to infinity. And so that one is there. And now if we can see the ranges as well. The range are the y values, but I could also just put the domain, use blue, of the purple function in for the range, and the domain of the blue function in for the range of the other one. So they switch. I'm just going to draw little arrows. And that's something that you can do. Okay, moving along. We have a few other things that help us figure out some properties of inverses. And so first, you guys remember the vertical line test from functions back in every math class since, I don't know, 6th grade maybe or before. So we use the vertical line test to determine if a function or an equation itself is even a function. Whether we can look in the graph to see if there are two inputs with, one input with two different outputs, that is not a function. Then we can also look at something called the horizontal line test, which we don't use to determine if something is a function, but it will tell us if the inverse is a function. Because when we reflect the function across the line y equals x, then it shifts, and so now it can be the horizontal line test to determine if the inverse is a function. And then one-to-one is, the definition is each input has its own unique output, and each output has its own unique input. And so let me just write those right here. That's part of each of these. Okay. So this one is each and then here we have the reverse or the switch, the inverse. And so if you put those together, then we have the one-to-one. And so I'm just gonna box this statement right here. So a one-to-one function is one that passes the vertical line test and the horizontal line test, and meets these criteria. And then basically a one-to-one function is a function whose inverse is also a function. And so I'm gonna write that next to it. Okay, so now we will move on to some pictures. So first I just want us to determine if the graph is a function, will the inverse be a function, and then at the end is that then one-to-one. So first, this first one definitely passes the vertical line test. But then if we put a horizontal line, it fails here and here and here and all over that whole area, so no. And then if there's one check and one X, then it's another X. There's got to be two checks for it to be one-to-one. So that inverse would not be a function there. Over here we can try it. It passes the vertical, passes the horizontal. Because we have two checks, it would be one-to-one. So now we know the inverse would be a function for this second graph. We can also do inverses algebraically. And so just remember the definition. Inverse is when you switch x and y. And so what we're going to do is, remember f of x is a fancy way of saying y. So the first thing we like to do is switch x and y. We're going to say x equals 2y minus 3. And then we want to solve for y. So switch x and y and then solve for y. So let's go ahead and do that. We're going to add 3 over, and then we will divide by 2. And then we'll write our final answer as a proper inverse function f -1 of x equals, and we can just leave it like this. So back to domain and range, we'll look at the domain of the original, which is just a linear function. We know from our basic functions that that has a domain of all real numbers, which I'm going to go ahead and put as the range of the inverse. And then let's look at the inverse function. That inverse function is also linear because it doesn't have any square roots or exponents. The variable x is not in the denominator. I don't see any absolute value sign, so it's also linear. And that means that the domain of the inverse is all real numbers, which we can now add for the range. So I could have done that at the beginning, or we can wait till the end. So find the equation of the inverse if we have f of x equals x over x minus 2. So we're going to do the same steps, but we do have now a rational function. And so I just want to model the steps for you since it might be some algebra that you haven't done in a while. So the first thing I would do when I have a fraction is I want to solve for y. And so I need to have no more fraction at all. And the best thing to do is just, multiply the y minus 2 over, or cross multiply, however you want to think about it. So I'm going to write x times y minus 2 equals y. And then we want to solve for y, but now the y is inside of parentheses. Whatever you're solving for cannot be inside of a parentheses. You need to get it out. And so I'm going to distribute the x. Xy minus 2x equals y. And now if I'm solving for y, what I'm looking at right now is that I have one y term on each side of the equal sign, which is not really ideal. We'd like for them to be on both the same side. So I'm going to move the y on the right side over, and then I'm going to move away the negative 2x to the other side. And I like to do this in one step. So I'm going to say xy minus y equals 2x. So I added the 2x over, and I subtracted the y. And what I'll do next is, now that I have the y's on the same side, I can take out the y. So I'm going to undistribute it or factor it out. And then last but not least, I can solve for it. So I'm going to have y equals 2x over x minus 1. And so again, I can rewrite this as a proper inverse so that I get full credit. All right, now let's go back and think about domain and range of all the original and the inverse function. And so for the original, I'll just kind of underline this in blue. Our domain was, remember, x cannot equal 2. We learned this the other day with our domain exploration in the breakout rooms. And so we're going to say negative infinity to 2 to infinity. And so I'm going to definitely add that down here for the inverse. And so now let's look at the inverse and look at the domain of that. Now I know, okay, well, x cannot equal 1. So we have negative infinity to 1, 1 to infinity. And even though we haven't learned range of rationals yet, we will next unit, I think. We then can now know the range of the original was negative infinity to 1, 1 to infinity. And if many of you have actually learned rational domain and range, and so you might have been able to figure that out already, which is great. But we'll talk about that in the next unit. Okay, moving along. I want you guys to pause the video and try these. When I do these, I'm not going to talk through them. I'm just going to put the work and the answer up. And so I want you to, I'll be writing it as I go, but I want you to pause the video, try it, and then see if you can get the same answers. All right, so I went through those pretty quick. Like I said, you should have paused and then now check your work with mine. Hopefully I didn't make any mistakes. Hopefully you didn't make any mistakes, and we're all good to move on. Okay, now here we're going to look at a situation with a square root. And so let's start with the domain of the square root. We know the domain is going to be x has to be greater than or equal to -3. So -3 to infinity. I don't need to write it down. I can put it here. And so I'm going to go ahead and put that for the range of the inverse. And then let's go ahead and find the inverse itself. So let's say I'm going to replace that with y. X equals square root y plus 3. Now I'm going to square both sides. Solve for y, so I will subtract 3. And my inverse function is going to be x squared minus 3. Now, what's the domain of x squared minus 3? It's a quadratic. The domain is all real numbers because we can put anything in. And so what I'm going to do right now is go ahead and fill that in. But then I want you guys to think back to what you have learned about the square root function. It is one of the parent functions that we did. This is a square root function that got shifted left 3 like this. And so this is what it looks like. Now, what I'm seeing now is a little bit of a problem because the domain of that is in fact 3 to infinity, -3 to infinity, but the range is most definitely not -infinity to positive infinity. So that is definitely not the range. So I'm going to cross that out. The range of the original function is really 0 to infinity, which if we use our rules for inverses, that makes this one also 0 to infinity. And so the reason why this happens is because, remember, here's the line y equals x. And so if I actually plot this x squared minus 3, should only really be plotting the right side of it. And that's because we found that by doing the inverse of a function that had a restricted domain and range. And so we have to consider how that affects the inverse function itself. And so this is what it would look like graphically. And so if you look, then I really should only be looking, I'm going to say, for all x is greater than or equal to 0. I have to add that to my answer because that way I can tell that this is the official inverse of that. This function didn't have a plus or minus in front of it, so it shouldn't have this extra left side that the x squared minus 3 would actually have. So when you have the square root function and you do the inverses, just consider that's a special case and think about the original domain and range and what that does to your inverse, and make sure you add this restriction right here so that your inverse actually matches what you started with. All right, so here's another example. We have f of x equals square root x minus 2. We're going to do this one a lot quicker. So we're going to do, I'm just going to work it out really fast. I'm really bad at writing inverse exponents. There we go. And so let's start back. We know the domain is 2 to infinity, which is the range of our inverse. And we know that the range was 0 to infinity, which is the domain then of our inverse. So I'm going to say for all x is greater than or equal to 0 to match. And so that's how that works. What you want to do is just always find the range of the original to help you decide what to do for that statement. You don't always need that statement if it matches. Okay, let's do the next one. Here we have f of x equals x squared minus 7. I'm going to replace that with a y. Say x equals y squared minus 7. We're going to add the 7. Now we're going to square root both sides to get rid of the squared. But when you're solving and you have to square root, that's where you have to do a plus or minus. And so what we have here is the domain of the original is all real numbers, which makes the range all real numbers of the inverse. And then now our domain of the inverse is -7 to infinity, which is actually the range of our original. Now, I just want to show you graphically why that happened. X squared minus 7 is just this graph down here. This is not 1, 2, 1. It fails the horizontal line test. So this inverse is not a function. What it looks like is we have x squared minus 7, square root, it goes up, and then we also have the negative version, it goes down. And so I'll make it an official inverse equation, but it's not a function anymore. This is two functions combined. And so that's why the range is all real numbers. If you look at the graph, it matches the original, but the plus and the minus. All right, we are almost done. We are just gonna do a little connection to the compositions that we've been learning. One way to determine if two functions are inverses of each other is to look at the compositions of each other. So we have f of x and g of x. We're gonna do f of g of x and then g of f of x, the compositions of each other, and then those are, they should equal just x by itself. If they both equal x, then they are inverses of one another. So we're going to start with f of g of x. So I'm going to say f of x plus 3 over 2 means I'll put x plus 3 over 2 in everywhere I see an x, and then I'll just distribute and get 2x plus 6. Or no, you know what I would rather do is just cancel out these 2's and have x plus 3 minus 3 equals x. So f of g of x equals x. So that one works, but we have to check both. Sometimes one will work and the other won't, and so we really have to check both to make sure. So now we're going to do g of 2x minus 3 really quick. And so let's see. We're going to put 2x minus 3 in for x plus 3 all over 2. And if I simplify that, I get 2x over 2. The 2's cancel, and so g of f of x equals x also. When that happens, then we say they are inverses of each other. All right, this one is the same one, so I'm going to move on to the last. Oh, that was the last page. There we go. So we have our inverse functions. Notes are now finished, and so what we did was we connected the compositions to the inverses themselves. If you did the algebra and found the inverses of each, they should equal each other too. But officially, when we want to say, are these two functions inverses of each other, we have to use compositions to do it. So I hope that you guys had a positive time listening to the notes and taking them with your PDF. We will have a lesson check on this tomorrow, and we will see you then. Thank you. Have a great day.